Hi, and welcome again to my Physics Online video lecture series. Today's video, we're going to be talking about current or current carrying conductors in a magnetic field. Essentially, what happens if you have a wire that has current running through it and you place that wire into a magnetic field? Recall from my earlier video where I introduced magnetic fields that you can determine the force from a magnetic field acting on a charged particle by using F is equal to QV cross B. That this is functionally equivalent to saying that the magnitude of the force, FB, is the charge of the particle times the speed of the particle times the magnetic field strength times the sine of the angle between the velocity vector and the magnetic field. So if I have a velocity vector in this direction and I have a magnetic field in this direction, then this angle counterclockwise from the first to the second term in the cross product, this is the first, this is the second, that angle is angle theta. The direction, for what it's worth, you find with the right-hand rule, and in this case, that direction is out of the screen towards you. So that is for individual charged particles. You could even do it on several charged particles and find the force on each one. What we want to do today is what happens if you have a bunch of charged particles in bulk. So let's say that I have a wire, and maybe this wire, we see a bit of it right here, and there's current running through the wire. So macroscopically, we'd say there's a current in this wire. Microscopically, what that means is that we have a bunch of charges within the wire that are all moving such that negative charges move against the direction of the current and positive charges are moving with the direction of the current. So you end up with some system like this where there are negative and positive charges moving. Again, microscopically the motion is kind of random, but on average this is what you have. Well, that means that if I have a magnetic field nearby, let's say that I have a magnetic field in red like this magnetic field can interact with all of these moving charges. I basically have this system right here, this scenario right here, QV cross B, over and over and over again for each of these individual charges. And note that if I have a negative charge, that's like putting a minus sign with the rest of this system. So if I'm going to draw forces on these charges, let's do it in purple. V is sort of upward along the screen. B is to the right. If I go up and to the right, I get a force that is actually into the screen. This one, I have a force that is into the screen. This one's negative. It's going downward and to the right. Down and to the right would be out of the screen, but since it's negative, this force also is into the screen. This force is into the screen. This force is into the screen. This force is into the screen. So I'm basically getting a bunch of little forces into the screen acting on these charged particles, and the charged particles are, they're free to move around within the conductor, but they're basically bound to being in the conductor somewhere. So collectively, these forces are all acting on the conductor. So treat these forces as acting on the conductor. And how much total force is there? So if each of these is acting on the conductor, the total force would be, well, just add all these little forces together. So total force just is sum of all the individual little forces. All right. Well, that total amount of force basically is going to end up being Q times V times the number of charges. So total force, let's do it in blue, total force is going to equal number of charges times individual forces, Q, V, cross B. Now we say, okay, V is the same thing as length per unit time, or distance per unit time traveled. N times Q divided by time would give current by definition. So this one right here we call length over time, and current, recall, is defined as basically number of charge carriers times charge divided by time, or in other words, total charge divided by time. So if you put all that together, what you end up getting is that the force on this current carrying wire, let's actually go ahead and copy the diagram over. The force on this current carrying wire is given by basically just the current times the length. So F is I times length crossed with magnetic field, ILB. And so that's your total force on the wire. This we usually rewrite as FB is equal to ILB, and again there's a sine theta term, where again theta is the angle between your drift velocity for the positive charges and your B field, although we put the vector sign over the length term in this case. So again, if I draw for myself a positive charge and it's going in this direction, this is the V, which ultimately gives you the IL term. This is the QV term. And then I have my magnetic field, which in this case is pointing in this direction, B. Then the angle theta is again counterclockwise from the first part of the vector, the L part, to the second part, which is the B part. So here's my angle theta. Note that the sine of that angle gives me a negative value, and that means that I have a force pointing into the screen as per our previously stated force rules. So that's force acting on a current carrying conductor in a magnetic field. We basically have time now to maybe do a quick example. All right, here's a basic example. We have a power line carrying, or a wire really, carrying 15 amps of current to the east in a location where the magnetic field strength is 54 microtesla. That's 0.54 Gauss for what it's worth. Oriented at 65 degrees below the horizontal and to the north. So to give you some idea of this magnetic field line, if this is due north, then the magnetic field line is actually pointing in this direction right here. So here's B. This angle right here is 65 degrees. That said, if I have a field that is, or a current that's running to the east, then this 65 degrees below north is actually in this direction. And so I have basically one vector this way and one vector this way. They're still perpendicular to each other. So B is still perpendicular to IL. Now, to get the actual answer to the question itself, this is asked how much force per unit length. So that would be F divided by L. Now, since F is IL cross B equals I L B sine theta, it follows that F over L is just I times B times sine of theta. Well, we just established that theta is 90 degrees. Okay, so this means that F over L is 15 amps times 54 microtesla times sine of 90 degrees. So we can put all those numbers into our calculator, although sine of 90, this term just is 1. And then 15 by 54 should be 81. So, excuse me, 810. So F over L is 810. And the units are, because we're in microtesla, that means that we're going to end up in micronewtons per meter. Or if you prefer, this is 8.1 times 10 to the negative 6 newtons per meter. So that's a simple example of this system. Going back to this diagram, as a reminder, if I'm looking at the angle that's happening here, this is 65 degrees, but my current is in basically this direction right here. So IL is perpendicular to B because B is within this plane entirely, and IL is pointing out of the screen at you. So as a clarification, why is theta 90 degrees? Okay, that concludes that example, and I think that includes our lecture for today. So hopefully you learned something from this short video, and thanks for watching.